Suppose the columns of A are linearly dependent. What does that tell us about the determinant of A times B? Well, the fact that A's columns are linearly dependent tells us something about the determinant of A. What it tells us is that the determinant of A is 0, right? That's the key relationship between linear independence and determinants. If A's columns are linearly dependent, well then the columns of, the standard basis vectors, that is the vectors 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, and so on and so forth, when they are all transformed by A, that n-dimensional cube that they create will have 0 volume. Remember, that's what the determinant measures. If A is a 2 by 2 matrix, well then the determinant measures the area of the parallelogram that results from transforming the standard basis vectors in R2, which are 0, 1, and 1, 0. So the standard basis vectors, they create a square with area 1. The determinant doesn't measure that. That's always 1. What the determinant measures is the area enclosed by A times 0, 1 and A times 0, 1. So like this area, for example, would be what the determinant measures for some 2 by 2 matrix A. Now, if the matrix's columns are linearly dependent, we're looking at this 2 by 2 case, A times 1, 0 and A times 0, 1 would both end up on the same line. Because in the 2 by 2 case, if A's columns are linearly dependent, well then the rank is either 0 or 1. The rank of A is either 0 or 1. If the rank of A is 0, then it is just the 0 matrix, and both A times 1, 0 and A times 0, 1 would be the 0 vector. Otherwise, the possibility is that A's columns span a one-dimensional subspace of R2, meaning A times 1, 0 and A times 0, 1 would both end up on the same line. Pretend this is A times 1, 0 and A times 0, 1 is over here or something. And there's no area enclosed by that parallelogram. Or there's no parallelogram here. So the determinant is 0 because the determinant is what measures that area. If we were looking at a matrix that is 3 by 3, we would be looking at the volume of the parallelepiped in R3 and so on. So anyways, the main idea is that if a matrix's columns are linearly dependent, and of course we're talking about a square matrix here, well then its determinant is 0. Then the question is, well, what is the determinant of AB? Well, the key idea we're going to use here is the fact that the determinant of a product is equal to the product of determinants. That is, the determinant of AB is the determinant of A times the determinant of B, which means that this has to also be 0, no matter what the determinant of B is. So the bigger takeaway here is that if A has linearly dependent columns, well then so will any product involving A. So if you multiply A by any other matrix, whatever matrix you get back will also have linearly dependent columns. Okay? And you can use the determinant of the product being 0 to reason about that. Okay? So that's what happens when A's columns are linearly dependent.